So welcome everyone to this talk, and I'll be talking about some improved guarantees for EFX allocations, and we would be establishing a connection to a problem in extremal graph theory. So without further ado, I will get started. So the problem that we are discussing here is a fair division problem, and in a typical fair division problem, the goal is to divide a set of items among a set of agents in a fair manner. So as you can see, there are two layers of ambiguity here, like what exactly are these items and what exactly I mean by fairness notions. So these things will become precise as the talk progresses. So before that, I would just say that several of our real life day-to-day scenarios are essentially fair division problems. So anything which involves a division of labor or household chores, or say distribution of vaccines, ventilators in a pandemic time, or if you want to settle divorces or manage air traffic and so on. And for more applications of the exact protocols used in day-to-day life, one can actually check this website, Split It. So with that, I guess I will get into the mathematical setting. So now I would be addressing the two ambiguous terms that I mentioned on the first slide. So in a typical instance of discrete fair division, you have a set of agents, a set of indivisible goods, meaning that these cannot be allocated fractionally. And each agent has a valuation function, which captures its utility for an allocated bundle. And we make an assumption that these valuation functions are additive, meaning that the valuation on a particular set is the sum of valuations of the individual items in the set. These are probably one of the most well-studied class of valuation functions in discrete fair division. And our goal now is to find a partition or a fair partition of the good set, x1 up to xn, where each xi is allocated to agent I. So now let's address by what I mean by fair. So quintessential notion of fairness is that of envy-freeness, right? So when, an allocation is said to be envy-free, as the name suggests, if there is no envy, meaning that no agent prefers another agent's bundle strictly to his own bundle. So for all pairs of agents I and I prime, I have that the agent I prefers his bundle at least as much as he prefers I prime's bundle. And once you define any notion of fairness, the first question we typically ask is that can we always satisfy this notion, no matter how large no matter how many agents, goods, or what kind of valuation functions we have, can we find an allocation which is always fair? In this case, the answer is pretty clear that we cannot. You can consider a small instance with two agents having positive valuation towards a single good. In any feasible allocation, this good will be allocated to one of the agents, and the agent who doesn't get a good would end up envying the agent who has the good. So as a result, we need to study relaxation. So EFX is not the first relaxation of envy-freeness that has been studied, but for the purpose of this talk, I will not be talking about the other relaxations. I'll focus on EFX. So here we say that, okay, now an allocation is said to be envy-free up to any good. If I look at two pairs of agents, I and I prime, it's okay if agent I prefers agent I prime's bundle to his own, because this is unavoidable as we saw in the previous slide. But the moment I remove any single good from agent I prime's bundle, this envy should disappear. So let me make it a little explicit with an example. So consider this small setting with two agents, and we want to divide a laptop, a bag, and a pair of shoes. And let's consider this allocation where I allocate the laptop and the bag to the first agent and the pair of shoes to the second agent. So this immediately doesn't seem to be the fairest allocation, and it indeed isn't. So consider the second agent, for instance. Its valuation for the pair of shoes is less than his valuation for the laptop, which is basically his valuation for agent one's bundle following the removal of a bag. So even after I remove one item from even after agent two removes one item from agent one's bundle, namely the bag, the envy still persists. So this is not an EFX allocation. So an EFX allocation will force you to something like this, where you allocate the bag and the pair of shoes to the second agent and the laptop to the first agent, or vice versa. So here you see that, again, the first agent is very happy. And for the second agent, well, he prefers the bag and shoes as much as he prefers the laptop. But even if you prefer the laptop more, following the removal of the laptop, the first agent's bundle becomes empty. So the envy would immediately disappear. So I hope the definition of EFX is clear. So that being said, we return back to our question. So as I said, once you define a fairness notion, the first question is, can we always be fair? And unfortunately, we do not know the answer to this question, and it's considered one of the important problems in discrete fair division. So I would just state a few results that are known. So again, there are existence of EFX has been studied in several settings, like say binary valuations, or when agents have identical valuations or two-valued valuations. So I will not cover all of them. So I just mentioned the ones where you do not make any assumption on the valuation functions other than additivity. So then EFX allocations is known to exist when there are up to 3 agents. And starting from 4 or more agents, this question is actually open. Okay, so with that said, I would like to say a few words about some of the relaxations. So again, there are more relaxations, but I only mentioned the ones which are important for the talk. So one of the relaxations is EFX with charity, where you do not allocate all the goods. So there exists, for instance, an EFX allocation with at most n-1 unallocated goods. So in the previous slide, I just said that it's open whether for 4 agents an EFX allocation exists. A corollary of this would state that if I do not allocate 3 goods, so no matter how many goods you have with 4 agents, if I can always pick 3 goods which will not be allocated, and the rest of the goods I can allocate it such that the partial allocation is an EFX allocation. And this bound was recently improved by Berger, Cohen, Feldman, and Fiat from n-1 to n-2. And another relaxation is approximate EFX, where following the removal of one good, we also scale down the valuation by some scalar alpha. And the current best known bound is 0.6, is the golden ratio. It's a result due to Amanatadis, Tokos, and Markakis. And now the question that we ask is, well, can we combine both of these? So can we combine both these relaxation to get another interesting relaxation? So namely, can we get any approximate EFX allocations with sublinear charity? So this is the main question. And we give a positive answer to this question. So we show that indeed this is possible. So we can find 1 minus epsilon EFX allocations with at most order of n over epsilon to the 4/5 charity. And we also do this in polynomial time. So our approach is constructive. However, the main takeaway that at least I would like to emphasize for this talk is that our technique is that we show that to get improved guarantees, you can actually talk about just a problem in extremal graph theory. And I will not be stating this problem in extremal graph theory explicitly. So the rest of the talk is structured in a way that I want to improve the charity on approximate EFX allocations, and you would see that this would naturally lead to this graph problem. Okay, so that being said, let me start with the reduction sketch. So I do some classification of the goods at the beginning. So I say that given any allocation X, so it will be a partial allocation where not all goods are allocated. I say that a good is valuable to an agent if the agent values that good at more than epsilon times his current bundle. Okay, and of the valuable goods, I further classify them into high demand goods and low demand goods. So the high demand goods, as the name suggests, are the ones which are the goods which many people find valuable. So the goods which are valuable to, say, at least D+1 agents. So the value of D, I would tell you exactly, later. And then there are low demand goods where each good is valuable to at most, say, D agents. Okay. And our algorithmic framework is very similar to the algorithmic framework that has been used to prove the existence of relaxations of EFX allocations earlier. So we always maintain a partial EFX allocations. And as long as there is some good which is not valuable, or if the number of high demand goods or low demand goods are large, then we can find a better partial EFX allocation, namely an EFX allocation where each agent is at least as happy as they were before, with some of them being strictly happier. So since we are always improving some kind of a welfare here, doesn't matter which welfare you choose, such a process will converge to an EFX allocation when these update rules are no longer applicable, meaning that it will converge to an EFX allocation when all the goods unallocated are valuable, and the number of high valuable goods and the low valuable goods are less than their respective thresholds. So you can see that the threshold for the low valuable goods is not explicit. It's some function of D. It's just R of D. I have left it here. And we'll make the R of D more explicit as the talk progresses. But the important thing is that we would finally end up with the number of goods going to charity as n divided by epsilon D plus R of D. By choosing the appropriate value of D, you can get an improvement over the linear bound in charity. You can get an improvement by this factor H inverse, where H is basically D times R of D. So for instance, if your R of D is linear, if your R of D is D, then you get an improvement of square root n, because each of these ends, d squared and h inverse is square root. And what we show in this talk is that we can get R of D to be D to the 4. And as a result, we can get a bound on Charity to be n over epsilon to the 4/5. Okay. So for the rest of the talk, I would just focus on this bound, because the other twos are not that complicated, and it can be, it would be also intuitive if you think about it. And this is the bound which establishes the connection with external graph theory. So to prove this, I just mentioned some standard concepts. The first concept is that of an NV graph. So given an allocation, an NV graph is a graph defined on the agents, and there is an edge from an agent I to an agent J if agent I envies agent J. And it's pretty much standard to assume that your NV graph is acyclic given an allocation, because if it is not, you can exchange the bundles along the cycle. The NV edges along the cycle would disappear. The agents along the cycle get strictly better bundles. So you can keep doing this process until your NV graph becomes acyclic. So this is a very standard assumption. And the second concept that I would be using is that of champions and champion cycles. So this is also a concept which was used in a paper earlier. I wouldn't be defining them precisely. I would just give you an intuitive definition, which is all that you would require for the purpose of this talk. So given an allocation X, I say that an agent I champions a particular set S if agent I is intuitively the most envious agent for this set. So there is a set S which many people envy given their current allocation. So let's say I host a competition like of envy, and the person who has the most envy is the champion. So that's all that you need to know. So there are definitions of what is a most envious agents are precise definitions, but you don't need to know that for the purpose of this talk. Okay, now what is a champion cycle? So this is the last, I guess, technical slide of preliminaries that we would need. So I say that an agents T1, T2, and T3, and the goods G1, G2, and G3 form a champion cycle if the following scenario holds. So you look at the components in the NV graph which contains these agents. So for instance, T1 is contained in the component of the NV graph which has S2 as the source. T2 is contained in the component of the NV graph which has S3 as the source, and the same for T3. G1, G2, and G3 are unallocated goods such that the following holds. So if I want to allocate G1 to the source of the component where T3 is present, then T1 is the champion. So T1 is the champion for XS1 union G1. Similarly, if I want to allocate G2 to the source of T1, then T2 is the champion. And the same, like if I want to allocate it to S3, then T3 is the champion. So then I say that we have a champion cycle. And a known result is that if you have such a champion cycle, then there is a way in which we can find an EFX allocation which Pareto dominates the existing EFX allocation, where you can make this improvement in the welfare like I claimed. Okay, so this is again a technical thing that you need to know. So with this, we can get started on our bound. So we introduced this concept of a group champion graph. So so I would be describing this graph, gradually. So let's say for our purposes that we have three goods which are low value, low demand goods. So G1, G2, and G3. And we define this group champion graph. So this group champion graph is a multipartite graph. Each part of this group champion graph would correspond to a good in LX. So let's take VG1. So VG1 is a part which corresponds to the good G1 in LX. And these vertices of this, in this part, correspond to the components in the NV graph, which contains the agents that find this good valuable. This might be a mouthful, so let me explain this graphically. So consider this simple situation. So you have the goods G1, G2, and G3. A1 and A2 find G1 valuable. A3 and A4 find G4 valuable. And A5 and A6 find G3 valuable. So you have this component containing A1 and A2 in VG1. You have the components containing A3 and A4 in VG2, and the same for VG3. And notice that since each good, so notice that we are in the case, so LX is low demand good. So each good is valuable to at most D agents. So each part here, each of VGI will contain at most D vertices, because each vertex corresponds to a component containing the agent that finds this good value. Okay, so each part has at most D vertices over here. Now, what are the edges between these parts? So there is an edge from a vertex in one part to the vertex in the other part if the agent, so for instance, let's look at this particular. So there's an edge from the component containing A3 to the component containing A1. If A3 is the most envious agent, when I give G2 to the component containing A1. So notice that A3 and A4 are the agents that find G2 valuable. So if I give G2 to any one of the sources, so let that be S1, S2, or S5, S6, the agents who will envy this would be the agents that find the good G2 valuable. Why? Because we are in the 1 minus epsilon EFX setting. As a result of which, for you to champion these bundles of the form XSI union G2, you need to find G2 valuable. Because you did not, I mean, if you don't find G2 valuable, you're not even going to envy this in the approximate envy setting. Because you did not envy the source before, you don't find the good valuable, so you're not going to envy the set XSI union G2. So the important thing to note is the champion edges that would result when I put G2 on any of the sources would be originating from the part VG2, because this is the part that contains the agents that find G2 valuable, right? So wherever I put G2, if you have champion edges due to putting this G2, it originates from VG2. Same goes for VG1. So whenever I put G1 to any of these sources, the champion edges will originate from VG1, because this is the part which contains the agents that find G1 valuable. And the same goes for G3. Okay, so important observation is that each vertex in one part has an incoming edge from some vertex in the other part. Okay, and what happens if I have a cycle that visits each part at most once? Basically a cycle which can contain at most one vertex from each part. This would imply the existence of a champion cycle, like I said. And this would imply the existence of an EFX allocation which Pareto dominates the previous EFX allocation. So now my question is, given the graph which satisfies the set of properties that I described, like the number of vertices possible in a part, the number of, like each vertex in a part has an incoming edges from the other part. The question is, how many parts can we have such that there is no such cycles? Because the number of parts corresponds to the number of goods in LX. So let me phrase this formally. So this is our question. We want to find the largest K such that there exists a K-partite graph. Each part has at most D vertices. And for any two parts, Vi and Vj, each vertex in Vi has an incoming edge from a vertex in Vj and vice versa. And there exists no cycle that visits each part at most once. So we call this number R of D, or rainbow cycle number, because you can actually color the edges outgoing from a particular part with one color. And the question is, the graph should not admit a rainbow cycle or multicolor cycle. And whenever Lx is larger than R of D, then we can find a Pareto dominating EFX allocation. So I just show you quickly that R of this number does make some sense. It's not meaningless. So for instance, let's consider the value of this number for when D equals 1. Then you cannot have more than two parts, because if you have two parts, then say vertex A2 in V2 will have an incoming edge from A1 in V1 and vice versa. And as a result, you have a two cycle which visits each part at most one. So R of 1 is at most 1. Using a similar argument, you can actually show that R of 2 is also at most 2. And what we show is that this R of D is indeed bounded, not just bounded, it's polynomial. It's order D to the 4, and this implies the existence of approximate EFX with sublinear charity. Okay, so with this, I would just state some immediate open problems and future directions which come from this work. So I feel that finding the correct upper bounds for the rainbow cycle number is interesting in its own right. It's a natural combinatorial problem, and it would be interesting to investigate. In particular, we suspect that the R of D is linear, and this would actually imply the existence of 1 minus epsilon EFX allocations with square root n over epsilon charity. And group champion graph, I feel, is a very natural variant when it comes to a generalization of the champion graphs and champion cycles. So a big question would be, can we find more sophisticated concepts than group champion graph, which would help us to find EFX allocations with charity, which is less than even square root n. So these are the main, I guess, open problems and future directions that stem out from the work. So with this, I would like to conclude the talk, and thank you for your attention.